Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Epen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@epen.info. My guest today is Professor James Kasting, who's a professor at Penn State University, where he holds joint appointments in the Departments of Geosciences and Meteorology and Atmospheric Science. His research focuses on the evolution of planetary atmospheres and climates, and on the question of whether life might exist on planets around other stars. In 2018, he was inducted into the National Academy of Sciences. His book, How to Find a Habitable Planet, was published in 2010. Welcome, Jim.
Oh, good to be here, Gil.
Yeah, thanks for doing this. So I want to set the context for our conversation with one of your older papers, which was as old as 1993, entitled Habitable Zones Around Main Sequence Stars. And I guess there is a rich history around this term habitable zones, right? It goes back to the 50s?
It actually goes farther back than that. It goes back to 1913. I only learned this a year ago.
Yeah.
So the term was brought up in a book by Walter Maunder, same Maunder from the Maunder Minimum and Sunspots. It was a book on the possibilities of life elsewhere.
Yeah. So he actually called it the habitable zone with the same meaning as we use it now?
With the same meaning, right. And then that was lost. It was Ralph Lorenz, a colleague of mine, who discovered that old book. And then the term was reinvented by Michael Hart in the late 70s. But there were other people who studied the concept under other names.
Okay. And so we use the term habitable zone to sort of indicate if a planet is in that zone around a star, it is habitable. Habitable in the sense that life could exist there, and life as we know it, I guess that's a qualification we have to make, right? Because we have only one instance of life that we know. But there are certain characteristics that makes that habitable zone. So in the 90s, what were the expectations of that?
Well, right. So first I would narrow your definition just a little bit. That the way I like to define habitable zone and the way Michael Hart defined it is the region around a star where a planet can maintain liquid water on its surface. Now, that does not mean that the planet is necessarily habitable, right? You could have planets with liquid water that were, for some reason, uninhabitable. They were way too hot or something, but just liquid water, and so that there's an assumption built in there that life as we know it requires liquid water. And so that assumption is built into that concept.
So if liquid water exists, though, Jim, wouldn't that automatically mean that the temperature has to be in a range that's useful?
Well, that's not quite right. Liquid water boils at 100 degrees Celsius
Hmm.
on Earth, but that's because we have a 1 bar atmosphere and the vapor pressure of water is at 100 degrees Celsius is 1 bar.
Hmm.
So that's why it boils. But if you can liquid water, if you raise the surface temperature on Earth, liquid water would continue to exist on the surface until you got up to the critical pressure, which is, critical temperature, which is 474 Celsius.
Hmm.
And most of us don't think that that would be habitable.
At least for the life we know, right? But for 400 degrees, I mean, we have this, what is it called? Extremophiles that live in fairly high temperatures on Earth, even, right?
They get up to, I think the record is now something like 125
Oh,
Celsius, but
that's
it's
all. Okay.
not 400 Celsius.
Okay. And so that's a narrow definition. So if liquid water exists, we call it habitable, but it doesn't necessarily mean that life can exist there. There are other characteristics too, I thought, like presence of oxygen and so on.
Well, oxygen is certainly not a requirement for life because we think that there was very little oxygen in the Earth's atmosphere for the first half of its history, and yet there's good evidence for life going back to at least 3.5 billion years ago.
Yeah.
Oxygen didn't go up until about 2.5 billion years ago.
Right. So oxygen was sort of a toxic waste of the life then, right? And then it changed completely.
It changed the environment entirely, right?
And so in the 1993 paper, so how would you? So that is a definition. We would call any planet that could harbor liquid water to be in the habitable zone. That's it.
At its surface, that's important qualification.
At its
So
surface. Okay.
at the surface, we think that there's several bodies in the solar system that could have liquid water subsurface, including Mars, Jupiter's moon Europa, and Saturn's moon Enceladus.
Mm.
But the key point is that if you're talking about exoplanets, it's very difficult to detect subsurface life. Whereas if you have surface liquid water, and therefore surface life, then that life can modify the planet's atmosphere in a way that you can detect remotely.
Okay. And so we can equate that to some sort of a distance from the star, right? So the astronomical unit is a distance between the sun and the Earth. And that distance where this habitable zone might exist is a function of the luminosity and I guess the size of the star, I would imagine, right?
Well, that's right. The luminosity of a star is related to its size and effective temperature. And the astronomers have studied that problem really hard, so they know the relationships quite well. But for a star like the sun, that's a G2 star, the habitable zone in our models goes from something like 0.95 AU. 1 AU is an astronomical unit, the mean Earth-Sun distance. So our habitable zones go from about 0.95 AU to 1.7 AU, roughly.
1.7 AU. So 0.95 AU. So at least without knowing a lot about it, that seems pretty tight. So if we move a little bit closer, we could be vaporized, so to speak.
That's right. And, that doesn't have to be the case. Our models are simple climate models in the sense that they're one-dimensional and they don't have cloud feedback. You can't do clouds well in 1D. So if clouds, there are papers showing that if you have planets that are slowly rotating and clouds build up on their sunlit hemispheres, then you can move the planet farther in and still have liquid water.
And 1.7 in the other direction implies that, so will Mars be touching that zone?
Yeah, Mars is at 1.52 AU. So Mars is within our habitable zone today. Yeah. But the surprise, Mars is not habitable. So that not at its surface. That's an example of a planet that is within the habitable zone, but is not habitable. And we think we understand why. It's lost most of its atmosphere. It's not volcanically active anymore, so it can't recycle CO2 into its atmosphere.
Mm. And so from an exoplanet exploration perspective, this is sort of a necessary condition, but it is not at all sufficient for us to even imagine the possibility of life.
Right, and it may not even be necessary. You can extend the habitable zone inward with clouds if you're fortunate. You can extend it outward with additional greenhouse gases besides water vapor and CO2, which are the two that we consider. But it's a region that is the most likely place to find a habitable planet.
This is obviously not practical, but with the environmental issues that we are dealing with, that is expected to raise the temperature of the Earth. If it moves little bit away from the sun, then we will be in good shape.
Well, that's right. So the sun is brightening with time.
Yeah.
See, that's another complication, is that the sun started out about 30% less luminous than it is today, and it's brightening currently at a rate of 1% every 100 million years. So in about 1 billion years, the sun will be 10% brighter, and that the habitable zone is therefore moving outwards. So the Earth will leave the habitable zone, and we may lose the planet's water starting about 1 billion years from now.
Right. And so when we look out into exoplanets, there are different types of stars, right? So F, K, and M, and so on. Could you give a quick explanation of how that categorization works?
Well, the names are historical. The astronomers at first didn't understand the relationships between they would take spectra of different stars, and they didn't understand the spectra until they'd studied it for a while. But once you understand it, though, it's a pretty simple sequence. The main sequence stars, which are stars that are burning hydrogen, fusing hydrogen in their cores, have a very well-established relationship between their mass and their surface temperature and their luminosity. So the more massive stars are much brighter. They're also bluer, and the less massive stars are much dimmer and redder than the sun.
Yeah. But this categorization, though, Jim, what is an F, K, and M? What do those mean?
FGKM. So an F star is a star that's a little brighter than the sun and a little bluer. The sun is a G star. It's a G2 star. You have G0s up through G9s, and the same for the other categories. And then stars that are a little smaller and redder than the sun are K stars, and stars less than about a half a solar mass are red dwarfs, which are also called M stars.
Okay, so the red dwarfs are smaller and less luminous, and so as we go from F to M, the habitable zone gets closer and closer. Is that the way to think about it?
That's right. In fact, one of the most interesting systems that we hope to observe in the next few years with the James Webb Space Telescope is called TRAPPIST-1. That's an M star. That's I think it's a very late M star, 0.08 solar masses, and the habitable zone, instead of being around 1 AU as it is for our sun, it's close to 1/10 of an AU. And the good news is there's at least 3 planets within the habitable zone of TRAPPIST-1 that they transit the stars. So they were discovered from ground-based telescopes, and that system will be a big target for the James Webb Space Telescope when it launches next year.
So what are the implications, Jim, of being that close to the star? Wouldn't radiation and other things? I'm again thinking about life, the possibility of life. Will it sort of exclude life as we know it that close?
Well, remember, you're by definition, you're getting about the same amount of sunlight
Okay.
that the Earth
Yeah.
receives. So that's not a problem, but you're actually onto something because M stars have more active, more magnetic activity and therefore stronger stellar
Mm.
winds. So one of the fears for M star planets, including the TRAPPIST-1 system, is that their atmospheres may get stripped off by the stellar
Mm.
wind. And actually, there's a whole host of problems for planets around M stars, which is why some of us would really like to be able to study planets around FGK type stars.
Right. And the orbital periods of this would be also pretty short, I would imagine, because it's close together, right?
Yes, I actually don't know the orbital periods of the TRAPPIST-1 planets, but they're much shorter than, much shorter than a year. Probably there's three of them, three or four of them that are within the habitable zone, and their periods probably range from days to a few weeks.
Days to a few weeks. Okay, so the whole season goes around in a few days or a few weeks. It'll be interesting to live on one of those things.
Yeah, but you might not be able to live on it. That's something that we're hoping to determine empirically by looking at those planets.
Yeah. And so is our current understanding then, if you assign a probability of life, is it the highest for a G-type star?
There's some argument about that, actually. There are people that think it's highest for a K star. But G stars, we have an existence theorem there. We know that there's at least one habitable planet around a G star.
Yeah.
Problem, if you go to the brighter stars, like the F stars, they have shorter main sequence lifetimes. They burn up their hydrogen fuel faster, and they also brighten faster as they age. So there's a real problem there.
Right. So you have to develop a civilization and get out of there a lot faster if you want to survive. Yeah.
That's right. Evolution has to be very efficient.
Right. So how much time do we have? We have a few more billion years, right, before the sun becomes a red giant?
Well, we have about 4 or 5 billion years until the sun becomes a red giant. But as I just mentioned, we have only about 1 billion years before the Earth could start to lose its water. And once it starts to go, it goes pretty rapidly. So we would have to geoengineer our climate to stay habitable for more than 1 billion years.
This is another area of your interest. So this is not in the paper, but I want to get your insights and perspective on this. And so this environmental problem that we're dealing with, it seems pretty bad. Are there geoengineering solutions that are being considered to get out of this nightmare that we are in?
Well, most geoengineers are worried about modern day global warming. And so they think about things like shooting sulfur dioxide up into the stratosphere and making sulfate aerosols that would reflect sunlight. But there is a much better idea, I think, if you have enough time to develop it. You can build a solar shield at the Earth-Sun L1 Lagrange point between the Earth and the Sun, and you can deflect the sunlight before it ever gets to the Earth. So there's some pretty well fleshed out ideas on that. It's very clever.
It has to be really big, right, to have an effect?
It does. It has to be about 2% of the surface area of the Earth, but you don't make it out of a single piece of material. Roger Angel at University of Arizona wrote a paper several years ago where he suggested you fly a lot of little sort of 1 meter, very thin discs that act like a Fresnel lens, and you need about 1 trillion of them, as I recall. So it's a big effort, but it's not as big an effort as building something the size of the Earth.
So you can build it in a modular fashion and essentially assemble it in space. if those things can actually produce electricity, it would be interesting. I don't know if there's a way to get get the power back to the Earth.
Yeah, I don't think Roger was thinking about that. These are very little flimsy things that their main purpose is to scatter sunlight away from the Earth rather than to collect it. The collecting sunlight is actually much easier than that. So we could do that from the ground with solar panels. There are proposals to put solar panels on the moon, and all that is much easier than building a solar shield.
Okay, so I want to go to one of your more recent paper entitled "Remote Life Detection Criteria: Habitable Zone Boundaries and the Frequency of Earth-like Planets Around M and Late K Stars." So we talked a little bit about this. So habitable zone, you say, around a star is typically defined as a region where a rocky planet can maintain liquid water on its surface. A rocky planet, so a planet which is water world with no hard surface on it would not be considered.
Well, a water world would have a surface. So we don't know whether water worlds would be habitable, but there's no problem in principle with that. The type of, you would have not an atmosphere solid planet surface, but an atmosphere ocean surface, and then there'd be another surface between the ocean and the planet. The type of planet that we don't think would be habitable would be a gas giant planet like Jupiter or Saturn, because there you never do encounter a phase boundary, and so there's no way to stabilize. Think about originating life. You need some kind of stable pressure temperature environment, and that's hard to come by on a gas giant.
This recent, I should call it speculation about Venus and possible life in the atmosphere. Is that possible that you have some sort of a life that is sort of floating?
Well, it's been proposed, and there was a big stir about a month or two ago when these papers came out announcing the detection of phosphine, pH3, in the Venus clouds. And I was all excited about that for a little bit. But now the critics have come out, and that the phosphine detection itself has been challenged.
Okay. So maybe a bit premature. And so in this paper, Jim, you also talk about sort of the interactions between CO2 and H2O, and it's a complex set of interactions, right? How the planet stays alive. You want to talk a bit about that?
Sure. The way I got into this problem actually was by thinking about the history of the Earth's climate. I mentioned that the sun was 30% less bright early on. That's been understood since the 1950s. And Carl Sagan and George Mullen wrote a paper on it that's been cited many times. Their paper was from 1972, when I was still an undergraduate. But that problem is called the faint young sun problem. A 30% change in solar luminosity has huge implications for climate. And, they pointed this out in their paper. And so the Earth's early atmosphere had to have a much stronger greenhouse effect than today in order to keep the Earth from freezing.
Right. And so then what happened? So that CO2 had to go somewhere for it to get to a state that we are in today.
Right. So the solution that I prefer, and actually most geoscientists prefer at this point, is that it was basically higher levels of CO2 in the Earth's early atmosphere. CO2 comes out of volcanoes, so you've got a good source for it. And that CO2 gets sequestered in carbonate rocks through the action of what we call the carbonate silicate cycle. So basically, CO2 enters the atmosphere from volcanoes. It rains out, it dissolves in rainwater and forms carbonic acid, and that dissolves silicate rocks on the continents and releases calcium and magnesium and bicarbonate ions that go into the oceans, and then organisms make shells out of calcium carbonate, and that makes carbonate sediments. So, and then finally, to complete the cycle, those sediments form on the ocean floor. At certain plate boundaries, the seafloor is subducted, carbonate metamorphism occurs, and releasing gaseous CO2 back through volcanoes.
So that cycle exists today. So when we get higher levels of CO2 into the atmosphere now, will that cycle accelerate? Is there any sort of balancing type activity that could happen there?
Well, it's not going to save us from global warming because it's too slow. So we're putting CO2 into the atmosphere on a timescale of decades to centuries. The carbonate silicate cycle takes about 500,000 years or so. That's its characteristic timescale today. So it won't save us from global warming. But the Earth has been evolving for billions of years, and so on that time scale, the carbonate silicate cycle is relatively fast. So it was perfectly capable of adapting to the gradually increasing solar luminosity.
And so global warming, it's too short. So what could happen is it could wipe out all life on Earth, and over a period of 500,000 years, it could sort of clear up through this process.
Yeah, I don't think global warming will wipe out all life, but it could make much of the Earth very uncomfortable for humans, and that's a serious problem. So I would not want to downplay global warming just because it wouldn't kill everything off.
So can we learn something from this natural process, Jim? I know carbon sequestration is something that is being talked about. This is sort of a carbon sequestration process, right?
That's right. Well, carbon sequestration, you can think of that as an accelerated weathering process. You're trying to store CO2 in the solid Earth in some form much faster than the Earth does that by itself, right? So that's a difficult problem. I think it can be done to some extent, but I don't think you can use that as the main solution for global warming.
This carbonic acid, the silicon cycle, is there something there that we could artificially do to sort of take CO2 out of the atmosphere?
Well, you're right. One of the geoengineering solutions is to try to pump CO2 into the right type of rocks. There are these ophiolites over in Oman that you have ultramafic rock that weathers very rapidly and could apparently store a lot of CO2. But then you have to liquefy the CO2 and ship it to Oman and then try to sequester it. I think it's all very expensive.
And you'll probably burn more fuel trying to do it.
Yeah, if you're running your ships on diesel, that's for sure.
And so this cycle gives us potentially a broader band of habitable zone, because if it goes in one direction, the cycle could bring it back to some extent.
Well, that's right. So, I got into this when I was a graduate student. I mentioned Michael Hart earlier. He recoined the term habitable zone, but in his model, and he did models of it, in his model, the habitable zone around the sun, the continuously habitable zone, the region that stays habitable over 4.5 billion years, only went from 0.95 AU to 1.01 AU. And in our model, the continuously habitable zone goes, out to about from 0.95 AU to 1.4 AU or so. So people the pessimists liked Hart's calculations because they said, Earth could be the only habitable planet in the galaxy. But in our calculations, we think that there could be billions of habitable planets.
Yeah, so just broadening that gives us a lot more options. So in the paper you say planets could exist, but we demonstrate that an inner edge limit of 0.59 AU or less is physically unrealistic. So are you saying we could go up to 0.6 AU?
No, that was, I think that was criticizing a particular paper that said that planets you could have a habitable planet at 0.5 AU, which is way within or 0.59 AU, way within the orbit of Venus. Venus is at 0.72 AU, and you can take one look at it.
Yeah, except for this phosphine, which is
except for the phosphine, right? So if there's life in the clouds, as the phosphine folks would tell us, then I'll have to eat my words.
All right, James, we'll take a quick break. When we come back, we talk about your other paper. Thank you.
Okay.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. Jim, we are talking about habitable zones, planets around stars, habitable zones more generally defined as planets that could have surface water. And it is the width of that zone is a function of how luminous the star is and other characteristics. And so, some of these planets in these habitable zones could potentially harbor life. So that is the interest in habitable zones. You have another paper here entitled Abiotic Oxygen Levels on Planets Around F, G, K, and M stars. So these are types of stars. And you ask possible false positives for life. So you say in the search for life on Earth-like planets around other stars, the first and likely only information will come from the spectroscopic characterization of the planet's atmosphere. And I know that there has been a lot of interest in finding oxygen, but your paper sort of details where oxygen could come from even without life. You want to talk a bit about that?
Sure. First I should say what we'd really like to find is oxygen and methane together, because that would be almost everybody agrees that would be a pretty reliable biosignature if they're both together. But methane in our own atmosphere is only present at low concentrations, about 1.7 parts per million, and so it would be hard to see remotely. Whereas oxygen or its photochemical byproduct ozone is pretty easy to detect by comparison. So that's why people, there's already a growing literature on the question of if you see oxygen or ozone on an exoplanet, does that mean that it's life or not, right? Or can you produce that oxygen abiotically?
Right. And so what are the ways a planet could produce oxygen without any life?
Well, one of the most obvious, to me at least, is if you have a planet like early Venus. Venus today, it's very hot and very dry, but we're almost certain that it started out with a fair amount of water, maybe as much as the Earth had, and then it developed a runaway greenhouse and it lost the water. Well, in the process of losing the water gets dissociated into hydrogen and oxygen, and most of the hydrogen escapes, but maybe some of the oxygen may escape, but most of the oxygen probably sticks around. And so early Venus could have built up a transient O2-rich atmosphere, which would not have anything to do with the presence of life.
Right. And so H2O breaking off O's and then O's getting together to make O2.
That's right.
And there are other ways you say oxygen could happen too, right?
Right. Well, if you look at Mars' atmosphere, atmosphere actually has something like 0.1% O2 in it today, and that is produced by photolysis of water vapor followed by hydrogen escape. But oxygen also escapes from Mars. If you had a planet about twice Mars size, Mars is about 1/10 of an Earth mass.
Yeah.
So if you had a planet that was about twice Mars size, then the oxygen wouldn't escape. You still might not have volcanism like you do on Earth. Volcanism puts reduced gases like hydrogen into the atmosphere, which soak up oxygen. So I've argued that a planet just outside the habitable zone, like early Mars, could build up abiotic oxygen if it was a little bit bigger than Mars.
Right. So is there an easy way for us to determine, I know, if we can assign a probability that the oxygen that we find is likely abiotic, then we can go to the next one. Is there an easy way for us to assign a probability that it is?
Well, that's why I started right out by mentioning methane, right?
Yeah.
There's always going to be skeptics out there, and if you just have oxygen, then not everybody's going to be convinced that it's biological. So we'd like to have another biogenic gas like methane or nitrous oxide, N2O, which is also almost entirely biogenic.
And so if I understood this correctly, Jim, you said CH4, methane is CH4, right?
That's right.
So methane is very small in Earth's atmosphere, and so it will be difficult to detect.
It would be, but it's not impossible to detect. And if we saw a planet, let's say we saw a planet just like the modern Earth around some nearby star, and we could see the oxygen, but we couldn't see the methane, I think we would be very motivated to build an even bigger space telescope that could get better spectral resolution enough to see the methane.
And so oxygen in combination with methane, you say, is a pretty good bet that it's biologic.
That to me is the best biosignature, and it's not a new idea. It was suggested about 60 years ago by Jim Lovelock, James Lovelock, the author of the Gaia hypothesis. So the idea has been around for a long time, and it hasn't really changed that much.
And there are no processes that we know of on Earth that could create CH4 without a biological process.
Well, there are. So there is some methane, very little from volcanism, but there's some from serpentinization, which happens. That's a process that happens when seawater flows through mid-ocean ridge hydrothermal vents. There's actually a variety of abiotic methane sources, but they're only a few percent of the biogenic methane source. So quantities matter.
Quantities matter. And once it's produced, it doesn't get broken up, right, by any kind of radiation or anything like that?
Oh, methane does. It's mostly destroyed by OH radicals, which are produced from reactions with water vapor. So the lifetime of methane in Earth's atmosphere today is only about 12 years. And that's one of the reasons why it's a good biosignature gas, because you have to be replacing it at a pretty fast rate in order to even maintain 1.7 parts per million.
Right. Yeah. So going back to our discussion on global warming, is methane also a culprit in this process?
Yes, it is. And you'll hear, if you read the IPCC reports, the Intergovernmental Panel on Climate Change, you'll see methane described as a very effective greenhouse gas, about 15 or 20 times that of CO2. But actually, that's only really true in an atmosphere like Earth's present atmosphere. Methane absorbs in certain window regions in the spectrum where CO2 and water vapor don't absorb very strongly. So one of the things I teach my planetary atmospheres class is that really CO2, if you think about it more broadly, CO2 is the better greenhouse gas. Methane is important on some planets like the modern Earth.
Mm. So can we use that process to suck that out, Jim? I'm trying for a solution, not to not to be fried soon.
Oh, for global warming.
Yeah.
Well, I think we should focus on the CO2.
CO2.
The methane.
Yeah.
The methane is already, it's being produced at a really rapid clip. You know, the two biggest sources are cows and rice paddies.
Right.
But we've already got, I think, 7 billion cows, and there's a lot of rice cultivation.
Yeah.
I don't think we're going to double that even. So if you double methane, you only get about a half a degree of warming out of it. Whereas if you double CO2, you get 2 to 5 degrees of warming. So
and CO2 is more permanent, right? It doesn't really go away like methane.
Right, it does go away, but on a variety of time scales, some as long as 500,000 years, whereas the methane hangs around only for about 12 or 13 years.
Okay. And so my understanding, Jim, is that we found something like 4,500 exoplanets out there. So, how many of them, or what percentage of them we believe are in the habitable zone?
Well, that's a good question. Many of these planets were discovered by the Kepler Space Telescope that was up from 2009 to 2013 on its main mission. It was looking for transits of planets across their stars. When the planet's orbit is oriented such that the planet passes between the host star, and the Earth. And the main purpose of Kepler was to answer the question that you just asked. What is the percent, what fraction of stars out there have rocky planets within their habitable zones?
Yeah.
The good news is that there's a paper, we've known the answer for M stars for about 4 or 5 years. Because the M stars, the Kepler data was much easier to process, and the answer is about 0.2. So about 1 in 5 M stars should have a rocky planet in its habitable zone. There was a paper submitted just 2 weeks ago to one of the astronomical journals. I know about this because my former postdoc, Ravi Kaparapu, is one of the authors on this paper. And they're claiming that
No worries.
Yeah. So they're claiming that the fraction of FGK stars that has planets in their habitable zone is even higher. It's more like 0.4 to 0.7.
Oh, wow. In the habitable zone. So
in the habitable zone.
Wow. So that's a big number. The M type stars that you mentioned, because of the close proximity to the star and because of solar wind and other issues, may have greater difficulty to harbor life. But that's not the case for at least G and K stars, right? So if you're finding 0.4 there, that's an amazing number of possible planets out there.
It's really exciting to me because, see, the Kepler data, the Kepler target stars themselves are not the ones you want to look at. They're mostly hundreds or thousands of light years away. But what we're interested in are the nearby stars. And so if the Kepler stars are representative of stars in general, then that means that the nearby stars also should, the nearby G and K stars should have a high percentage of rocky planets in their habitable zone. And that's really exciting.
Yeah, so there is a mission in the works, right? Is it TESS or something?
Well, TESS is up there. It's looking for transiting planets, which can be observed by the James Webb Space Telescope. But most planets do not transit. Think about most planets do not transit. Think about in order for it to transit, transit its star, that means the plane of the planet's orbit has to be aligned with the Earth, so that the planet passes between the host star and the observer. And if you look at our own solar system from a large distance at any arbitrary angle, you only have about a 1 in 200 chance of seeing the Earth transit, which means that you would have to look at, even if every one of them had an Earth around it, you'd have to look at 200 stars before you would see one Earth transit.
Yeah.
But if you, so that's because you're looking for transits. But what we really want to do is build some big space telescopes that can do something called direct imaging, where you look for reflected light from the planets, and then they can be anywhere around the host star. They don't have to be in a particular orbit.
Right.
So that's the real goal.
And so, if I understand this correctly, Jim, Kepler went up there and looked in one direction, right? And looked deep in one direction. And so
That's
what
right.
you're saying is that, so we now have an estimate of what percentage of the planets could be in the habitable zone, and it's a very high percentage. And so now we can look around in close neighborhood and find those planets if we can, as you said, direct image them. And it seems like it's a pretty profitable venture, because if you have 40% chance of anything that you find is in the habitable zone, that seems like a very interesting thing to do.
Oh, well, I agree. And, the astronomers are, as we speak, carrying out, every 10 years, they do a decadal survey where they prioritize big missions for the next decade. And two of the missions they're studying would be direct imaging missions. One is called LUVOIR, the Large UV Infrared Optical Telescope. I got the wrong order on that. And the other one is called HabEx, the Habitable Planets Explorer. And both of those would be able to look at dozens of stars close to the Earth and search their habitable zones for rocky planets.
Yeah, but on the pessimistic side, though, Jim, it also means that. So let me ask you this: so, what would be sort of the distance that you'll be looking at from the Earth for such a process?
The ones that would be studied by HabEx and LUVOIR would tend to be within about 40 or 50 light years of the Earth, and there's several thousand stars if you count the M stars in there, but their best targets are actually FGK stars. And so there's several hundred stars. There's different versions of these telescopes, and they can all sample different numbers of stars. But you could get a sample anywhere from about 20 or 30 for the smaller missions up to 50 or 60 for the larger versions of these telescopes.
Yeah, so I was thinking 40 to 50 light years away, that zone, we have been transmitting TV signals into that zone. We haven't heard anything back from anybody. So it seems like we at least don't have any sign of advanced civilization in that zone.
Well, that's correct. And but we don't, there's many uncertainties here, right? It may be that simple life is common, but intelligent life is not. That's one hypothesis, right? And there's lots of speculation on this, but the only way to really address that speculation is to go out there and look and see if you see any signs of life.
Right. And so in conclusion, Jim, based on everything that you know, everything that you're doing in this area, what is your gut feel in terms of, will we find, we have already found, I would think, very good habitable planets, right? Right size, right temperature, harboring water. So it seems like we found many that has the right characteristics. What is your guess that simple type life exists there, or we don't really know?
Well, I was a fan of Carl Sagan when he was alive. He was one of my, an inspiration to me as an undergraduate and in graduate school. And so Carl was very optimistic about this. I'm very optimistic about it. And I think that the way we'll really find the answer is if and when we build one of these big direct imaging telescopes. And I think we'll know the answer then within a few years after
So
that.
these direct imaging telescopes, they will be able to get a very detailed spectrum so we can actually get a composition of the atmosphere.
That's right. They can get a much better spectrum than the James Webb Space Telescope will be able to do, because getting transit spectra of rocky planets is difficult. But with direct imaging, you're looking at reflectance spectra. So you're looking at reflection from the whole planet's surface, not just transmission through the thin atmosphere. It's much more effective way of getting a spectrum.
So do these reflections also tell us, I'm just thinking, I don't know, could we hypothesize around clouds and how things might be moving, or that's too much?
Well, clouds are sort of an interference, actually. They partially obscure the spectra of the gases, but closely related to that, though, it turns out that if you can take a time series, you stare at one of these planets for, say, a few days. Let's say it has a day length like the Earth of 24 hours. You can actually figure out the rotation rate by looking at the spectra and how they repeat over certain time scales. And you can even figure out things like the percentage of continents and ocean, because continents are redder and oceans are bluer, and you can tell that from the spectra.
That's really interesting. So let's hope that we find one, Jim, close enough with a welcoming civilization, because we may have to get out of here at some point.
That's right. My colleague Sarah Seeger at MIT, who's one of the leaders in this field, calls it the second Copernican revolution. That's what will be triggered if we find other planets out there.
Right,
like
right. There's some engineering issues we need to tackle, but maybe the standard model will change by then. But excellent. Yeah, this has been great, Jim. Thanks so much for spending time with me, and good luck with this research.
Okay. All right. Thanks a lot.
Bye. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.